All right, as I said, I've got kind of a nice example here. This is from another text. This is from Morin and Shapiro, I think the fourth edition. It's actually my text when I took thermodynamics. I'm going to switch cameras here. You guys know how this goes when I do an example problem. I'm going to write these out, the givens here. This is a turbine with water, so that it says that steam is flowing through it. And again, I'm not going to solve this out. I'm going to set it up and I'm going to work through it with you and get you to a point where you can solve it out. My hope is we're at that point with you where you can work it out reliably on your own. All right, and so you can read through it here. Steam enters a turbine with a pressure of this text likes using bars. This is 30 bar. We'll talk about converting that in a second. With a temperature of 400 degrees C and an inlet velocity of 160 meters per second. Saturated vapor at 100 Celsius exits. So I'm going to say X2 is equal to 1. That's a shorthand way of writing saturated vapor. X means it's saturated. 1 means it's 100% vapor. X2 is equal to 1. T2 is 100 degrees C. So at that temperature and the fact that it's saturated, anything means it's basically coming out at atmospheric pressure because water boils or is saturated at 100 degrees C. Also, they give us an exit velocity. So this is one of those problems where I'm going to go ahead and account for the change in kinetic energy. This text says at steady state. For our text would call that steady flow. But they're saying at steady state, the turbine develops work equal to 540 kilojoules per kilogram of steam. So this is lowercase w out, right? Lowercase w out, that is work per unit mass. That's 540 kilojoules for every kilogram of steam. Heat transfer occurs between the turbine and its surroundings at an average outer surface temperature of 350 K. So you have a surface temperature, 350 kelvins. They want to know the rate at which entropy is produced within the turbine per kilogram in units of kilojoules per kilogram Kelvin. So they want us to find little s gen is what they're asking. Oh, sorry, you can't see that. In this text, they would actually, in many texts, they would use a lowercase sigma to call that, to refer to that. This is a turbine, by the way. All right, so I'm going to stop sharing. We've got what we need here. And this is lecture 21, page 1 of something. A lot of texts would call this lowercase sigma. This particular text we're working this example problem out of would use the lowercase Greek letter sigma to represent the entropy generated. Our text likes to use sgen, and that's perfectly okay. So we want to find the entropy generated. And so how I would always say, okay, what's a good tool or where should we start? The gag reflex often is we would start with the first law. But I would suggest to you, you're looking for sgen, it might make sense to start with the second law. So here's what I would challenge you to do. I would challenge you to pause this video right now and write for me the first and second laws for this particular problem, and let's see how you do. Okay, so go ahead and write first and second laws for me, pause, and then come back. And I'm going to pause because I'm going to write them also. So, all right, how'd you do? Well, and I'll tell you, I went ahead and simplified both the first and second laws down. So I've solved for little s gen, and I went ahead and solved the first law for the term that I needed to go ahead and finish the second law. Some of you guys have some of my students in my class and have emailed me and said, well, I understand like what you're doing when you work it out, but when I go to do it, I don't know what to do. And that's why I'm saying, hey, pause the video, work this problem out, see how you do. And then when I show you a few steps, feel free to pause it and see if you can, if that changes, like if I did something different than what you did, go back and rework after you see something that doesn't match what you have. Go ahead and pause it and try to work through it another time rather than watch me go ahead and show you the whole solution here. Um, Challenge yourself. That's the only I always tell students, problem solving is a skill, no different than any kind of skill about playing any sport, like basketball, for example. Let's say free throws. You can watch me shoot free throws all day long. I can explain to you exactly how to shoot free throws. I can show you me shooting free throws. Does that mean you're going to be able to shoot free throws? No, no, it does not. You have to actually do it. So you have to practice it. I'm explaining to you how to shoot free throws. You have to actually shoot free throws. And that's the reason I tell you, pause it, work it out, and then let's compare. Okay. So I'm going to show you, line by line what I've done, right? This is the version of the second law that I started with. You don't have to start with this version. You could start with the per unit mass version, but they've asked for little s gen per unit mass entropy generated. So this is the second law, general, with a mass flow rate, or everything's measured per unit time. Now we simplified this, or if we look at this and say, okay, what do we know here? Well, I know state one and state two. I know P1, T1, I know X2, T2. So I know S1 and S2 because it's water. So I just look these up in the property tables. I don't know M dot, but everything in the problem is actually being asked per unit mass. I'm looking for S gen. I need to quantify this thing. Well, what do we know? We know that there's a constant average surface temperature. So I can actually pull that out of this integral. And this is one where we can just simply say, well, you know what? This integral, because that heat transfer is occurring at a constant temperature, and it's going out, it's losing heat. So it's minus Q dot out divided by the temperature of the surface. That takes the place of this guy. So it's minus Q out over T surface. Again, if you didn't get this far, pause it and go ahead and use this and see, go ahead and try to work the problem out. Get it set up to where all you got to do is look up property tables and run through your calculator. All right. Okay. You ready? You want to keep going? Okay. So what do we do with that? Well, let's solve for what we're looking for. Solve the second law for what you're looking for. You're looking for little s gen. How do we find that? Okay. Now I know, again, I know S2, S1. I don't know M dot, but let's see if we can work around that. But I do know the temperature of the surface, and that means I do now need to know the heat transfer. So now heat transfer becomes my unknown because this is what I'm looking for. Now I've got a second unknown, a sub-problem I've got to solve. So how do I find heat transfer? So what do you think? What is a good tool or law or relationship I might try to use to find an unknown heat transfer? And hopefully you guys are screaming at the screen right now. First law, all right? Absolutely. And I asked you earlier, go ahead and write down your first law. What does your first law look like? Draw your system. Got a turbine here. It's got mass coming in, mass going out, heat going out, work going out, or power output. Your first law should look like this. I do have a kinetic energy change because they gave me an inlet and an outlet velocity. So I want to go ahead and include that in addition to the enthalpy change. Let's figure out what of these we know, what of these we do not know. We know work per unit mass. That was given to us. This is little w, that is power out divided by m dot. All right, so that's known. Um, so what I can do is I can divide the whole thing by m dot. These terms all now just end up the same. The m dot goes away, but then I know little w out. And notice here, I don't need to know q dot out, or I don't need to know m dot. I just need to know their ratio, right? So I'm going to go ahead and solve the first law for little q out. That's heat per unit mass. Notice I know this. I know these. If I can find s's, I can find these. Little q out becomes my unknown. You can plug that in here. S gen becomes the only unknown. Out of a 15-point problem, excuse me a second. Out of a 15-point problem, I had to close my office door. Sounds like they're giving a tour outside. You would probably be at 16, 17 points because what I would do is I would say, okay, well, it's a second law problem, so I'd probably put this would probably get you like 8 points. This would get you 7 if they're correct. Showing me you know how to get to a solution. Hey, I'm looking for S-gen. Here's how I get it. I need to know this. Here's how I get this. I mean, you basically have solved the problem out. I would normally put 5 points towards getting to a solution. I would give you 2 or 3 of those 5 points right here before you even bust out a calculator. So you're at like 17, 18 points. That's a C at this point, if it's all correct. Show me you know how to find properties, right? Show me you know, hey, I'm going to use P1 and T1 to get H1 and S1, and I'm going to use T2 and the fact that it's saturated vapor to get H2 and S2, right? And just doing this, I would give you a couple of points for that. I would give you a total of 5 points for getting me all these properties. Normally is how I'd set that up. So, you're at like 22 out of 23 if you get these properties. Just right now, you're basically at 18, 19. Go get these properties, you'd be like 22, 23 points before you actually bust out a calculator. That's how I grade because I'm grading you on your ability to show me you could find solutions to problems. Because I'm training you to be engineers. That's what I want you to do. Right. All right. I don't have an answer to this. You know how to look up if you don't at this point, if you don't know how to go look up properties and you don't know how to plug these in and run numbers, I don't know why you're still enrolled in an engineering thermodynamics course at this point. You need to try again. But at any rate, I feel like I'm being harsh when I say that, but I'm being honest with you. At this point, you should be able to look up properties. If you're just joining us on the internet and you've randomly stumbled across this video and you've stuck with us this long, hey, congratulations. Go back and watch previous videos if you want to know how to actually get to an answer. All right, guys, I'm going to stop there. I'm going to get these posted.